Okay, great. So I'm going to try and be quicker to get back on time. First off, I want to explain what space weathering is for those of you who don't know. So the surfaces of airless bodies such as the moon are exposed to high energy interplanetary environment. The surface is exposed to processes such as micrometeorite bombardment, which results in vaporization, comminution, and melt splash, which adds to agglutinin formation. We also have exposure to solar wind, which results in sputtering and solar wind implantation. Collectively, these processes result in chemical and structural alterations of regolith exposed at the surface. Many such features can be observed via transmission electron microscopy. So this is a lunar northite that was embedded in epoxy and sliced at 50 nanometer thick thin sections. It's a scanning TEM image, bright field mode. And the features we're interested in are on the very rim. So if we move to the right, we first see a bright field stem image of the rim. In the blue bracket, we have a melt splash with the little black particles. Those are your nanophase iron particles. And then the yellow bracket denotes the grain interior. If we move to dark field stem, we see some additional features. Again, we have our melt splash, except the nanophase iron particles are bright. And then in the grain interior, we have a solar wind damaged rim that's mounted in green here. That's formed through low energy solar wind ions, primarily hydrogen and helium, that can penetrate nanometers in depth beneath the surface. And just below that, we have solar energetic particle tracks that are traced in red. Those form through higher energetic particles from the sun, primarily iron group nuclei, and they can penetrate millimeters in depth beneath the surface. Just below this, we have a energy dispersive X-ray spectrographic chemical map. We have a magnesium-rich melt splash on top with the embedded nanophase iron particles, and just below that, we have aluminum, indicative of our lunar northite. For the remainder of this talk, I'm just going to focus on the solar wind damaged rims and the solar energetic particle tracks. So previous track studies relied on a preparation technique known as chemical etching, by which researchers would polish grains and then coat them with some corrosive material to broaden the widths of these tracks so that they could be observed via scanning electron microscopy. And with it, they were able to produce these calibration curves, just showing how track density changes with depth, and found that track density decreases very, very quickly with increasing depth from the surface of a grain. And from these studies, they were to apply it to studying lunar soils. So, for example, if a lunar soil had a high number of grains with high track densities, say 10 to the 9 tracks per centimeter squared, that's associated with solar energetic particles, which have a very high production rate, and hence this regolith would be considered surface correlated. On the other end of the spectrum, we have a high number of grains with low track density, so 10 to the 6, 10 to the 7 per centimeter squared. Those are associated with galactic cosmic rays, which produce at much lower rates and can penetrate centimeters in depth. So this regolith was likely never exposed at the surface. And then we have intermediate distributions, which are just various degrees of mixing. So we have these distributions, but for mature regolith, this distribution, there was a limitation to this etching process that they were utilizing, by which you would broaden the rims of these tracks, but for very high track densities, you would be unable to discern one track from another. So there was a limitation. They really capped out at 10 to the 9 tracks per centimeter squared. So this tells us whether regolith was exposed at the surface, but it tells us nothing about the degree of maturation or anything about the surface exposure timescales. Recent work by Keller et al. 2021 was able to observe these higher track densities using modern TEM techniques. Some examples of these high track densities are shown here. We have 10 to the 10, 10 to the 11 tracks per centimeter squared, and a very high track density grain here. And with this was able to develop a new production curve, as well as a new track production rate of 44,000 tracks per centimeter square per year. So again, we have our solar wind damaged rim, and we have our solar energetic particle tracks. In the same paper by Keller et al. 2021, they were able to relate the two and showed that solar wind damaged rim widths increase fairly quickly over the course of about 10 million years before leveling out. However, energetic particle track densities continue to increase with increasing exposure age. So this is a plot showing lunar and northite grains. So I want to apply this to 73002. You probably all know about its origin by now, but just a refresher, it was collected at Station 3 atop the Young Light Mantle deposit. This is an image I'm sure you're all familiar with, and you're also probably very familiar with the dark lithology bounded by the light lithology. So the dark material, that is space weathered material, and that was confirmed with optical maturity profiles and ISOBES over FEO profiles. And so if space weathering occurs at the uppermost surface, well, what is bringing this material downwards? And the answer lies in gradual reworking. So as small reworking processes happen at the very top, material will slowly work its way down and only to be replaced by immature regolith, which will then be exposed. And then it's like a cycle. And this is called the in situ reworking zone. And so I'm curious to know at what degree is regolith exposed at the very surface before being worked downwards through this in situ reworking process. So Purdue received the top 8 intervals or top 4 centimeters of material. And then every fourth interval after that, we received them as sub 45 micron size fractions. We sieved them down to sub 20 micron size fractions, embedded them in epoxy, sliced them at 50 nanometer thick thin sections, and then took a bright field and dark field stem images. We counted tracks within a half micron of the rim, and then drew 100 by 100 nanometer square areas around the densest regions, and then used our track production rate of 44,000 tracks per centimeter square per year to determine our exposure age. We directly measured the rim width using digital micrograph analytical software, and we restricted our analysis to olivine and anorthite grains, as those are the most well constrained for this kind of work. And that was those mineral phases were identified using energy dispersive X-ray spectroscopy. So far, we've looked at about 30 grains for interval 1 and anywhere from 5 to 15 grains in intervals 2 through 8. The oldest grain we found was about 11 million years, and that was found in interval 1. And then the second oldest grain was about 8 million years. That was found in interval 6, so 3 centimeters in depth. The majority of grains we found range between 1 and 5 million years worth of exposure. In relation to the work of Keller et al. 2021, we see a similar upward trend with rim thickness versus exposure age versus track density. So a different way to look at this is through a histogram. So this is a histogram of interval 1. So we have the vast majority of grain densities, or the majority of them concentrated around 1 to 2 times 10 to the 11 tracks per centimeter squared, which is about 4 to 5 million years worth of exposure. And then when we compare that to all the intervals together, we see a similar trend, again, 4 to 5 million year exposure age peak here. And then grains of higher densities becoming more and more rare. Some examples of these track densities are shown here, where we have 1.53 times 10 to the 11 tracks per centimeter squared, corresponding to about 3.5 million years of exposure. And we have our highest track density, corresponding to 11 million years of exposure. Now, you also might want to take note that the high track density grain has a much wider solar wind damaged rim than that of the lower track density grain. All right. So what does this all mean? Well, with this updated ability to observe these high track density grains, it's possible to understand the degree of maturity in a soil, as well as understand the distribution of exposure ages in a particular soil as well. Now, to conclude, like I said, the additional two orders of magnitude afforded by modern TEM techniques allows us to have more refined analysis of what mature regolith is and how it's distributed on a grain by grain basis. So the perspective of the grain. The distribution peaks at track densities around 5 million years of surface exposure. And Dick mentioned before that the in situ reworking zone could have developed up to about 17 million years, as low as 10 million years, depending on how you look at this non-lunar mechanical mixing. So we're going to be, so this 5 million year surface exposure is a testament to the high rate of mixing going on in this upper region, nonetheless. We're going to look at, we're going to, all I want to say was we're going to be looking at all the intervals, the remaining intervals that we've seen so far, as well as our goal is to get about 30 grains from each interval. So we're going to continue working on the in situ reworking zone. That's all I have, and thank you.